So be careful, we are not looking at the graph anymore here. We are just looking at the objective function because basically we changed the calibration method. Before it was a manual calibration, so it's better to look at the hydrograph. In this case, it's an automatic one. Still, it's not automatic, but it's going to be automatic. And therefore, we don't need to see the hydrograph. Okay, good. Now the next step is allow the PC to find the best value of C by minimizing the sum of squares. This is the next step. At this stage, we need a package. We need an algorithm. And this algorithm, there are several optimization algorithms. They are called optimization algorithms. And sometimes you may find synonyms of this, like minimization algorithm. It's better to use optimization because the optimum could be the minimum or the maximum. If you use the net efficiency as objective function, the optimum is in the maximum. If you use sum of squares, the optimum is in the minimum. So R has embedded in it several optimization algorithms. Besides those that are already embedded in R, you could decide to use others optimization algorithms, because there are many, several. And of course they have different behaviors, and let's say that it's also a matter of personal preference. But your question, of course, would be, in this case, if I want to use an optimization algorithm that is not embedded in R, how can I install it? You need a code, and you need to use the code in R. So be aware that R has embedded a lot of packages, but it has embedded just what they thought to be the minimum necessary. Because the community developed a lot of packages for R. And you yourself, once that you develop a code, like the code for the application of the IMOD model, you may decide to make it available in R, because R is open. You just have to obey some rules. The people that are maintaining the R package, they want that if you make a software available, they want that you write an help with the format required by R. They want that you explain everything of it in a clear manner. But once that you develop a software which is clearly explained and meets the requirement, you can make it available. And the result is that there are libraries, official and unofficial, of plenty of codes for R. And they are not embedded by default, because, as I said, the developers thought to embed by default only the most used packages. Why that? Because you may say, why don't embed by default everything? Because otherwise the package gets too big in terms of occupancy of the hard disk, but also in terms of time required to start the package. If you upload a lot of packages, then when you start R, it becomes slow. And also R itself, when making the computations, becomes slower. So you shouldn't install everything. But once that you have a need, and in this case the need is, for instance, we artificially created it, I want to use an optimization algorithm that is not embedded in R. So once that you have a need, you don't have to hesitate to install an additional package. And this is indeed needed very frequently, because we are dealing, our science is hydrology. Hydrology is not very popular. If you are dealing with mathematics, then in R you find everything. And in particular statistics, you find everything. But for hydrology, of course, they didn't embed a lot of packages, because, you know, hydrology is not so popular. But in this case, the need is different. It's not really hydrology, it's optimization. But in any case, it's important that you learn now how to install additional packages in R. And the specific case is an additional package which is available in the official R repositories. So a package that was developed by the community but met the requirements for being included in the official R repository. So basically, if you use these softwares, you are reasonably sure about their reliability, reasonably. Instead, if you pick up a software for R from the web and you don't know anything, you just open a web page, you see the software and you install it, you have to be very careful, of course. But in this case, if we pick up the package from the repository, that's fine. Okay, first of all, you need to know what you are looking for. So what is the name of the package that you want? So basically, if you wanted an optimization algorithm, what I do usually, if I don't know anything, what I do is I go on the web page, on the web, and then I go over Google, and what's this? Yeah, they changed something. Advertising. Yes, that's fine. I go over Google and I write optimization. Unfortunately, optimization can be spelled with the Z or the S. Let's use the Z, which is more common. And then you need to write R project because, you know, otherwise you find everything for optimization. And you can't write just R because R is not a useful search term. Okay, and you see here a lot of entries. Optimization packages for R. Optimization and solving packages. These are official R sites, Forge, R-Forge, and CRAN. And of course, you don't need to stick on that, but the title looks promising. Let's see. Be careful, another thing that is not absolutely related with the academia. Being quick and efficient in searching the web gives to you an added value which is enormous. So, you know, the web contains everything, but unfortunately much more than everything. So you need to be able to select. And if you are expert in this, because there are tricks, try to gain experience. Because really, when you make your profession, it's absolutely needed to search the web. And you know, once that you start searching, it can take easily hours or minutes if you are efficient. So this is another thing which is really important. And a good opportunity could be the thesis. When you have to, for instance, to write your thesis, and you have to write a chapter on the state of the art, then I always suggest students go on the web and find references, articles, Google Scholar is very helpful. But of course, if you write water resources management, and then you search on Google, you find like 200,000 of entries, and then you have to be able to select. So you need some tricks. And it's difficult for me to explain how I do. First of all, I'm not sure I am efficient, but indeed I realized that over the years I learned how to optimize the time that I dedicate to web searching. I'm not sure. There was a course once that was given by the library, the Dore library, on the web searching. Okay. And unfortunately, you see that there are a lot of packages, and that's fine. And then, of course, I give to you, if I'm not able then to find the best one, because there are too many of them, usually I ask people. So I go to my students usually and I say, look, I need an optimizator, so what are you suggesting? And then I have a student that is very good in R, and he suggested me to use, let me see if it is here. No, it is not here, I don't know why. But he suggested me to use a package which is called DE-Optim, sorry. And indeed, I found it very helpful. Uppercase, lowercase, which means differential evolution optimizator. Let's use that because, then we have a discussion with colleagues because we are working now on calibration of several rainfall models, and some colleagues told me that they were not fully happy with this package, but let's use that because for our purposes it's fine. Okay. So, how to install this package, given that I know already that it's in the official R repository. So, the instruction is install that packages. And then, if you know the name, DA-opt-in. I'm not sure it works now, let me check. Yes. I get this warning. Let's see. Just 1 second. Okay, I need to define this is just a technical problem. I need to define a personal library. And okay, let me define it. Yes. Okay. And then you see that he says, please select a CRAN mirror. What is CRAN? It's an acronym, I don't remember what it is, but it's a site that collects open software where R is available for download. And given that this is a site that gets a lot of accesses, people created a lot of mirrors. And the mirrors basically are copies of the website in order to split the number of accesses from the web. And usually I take the mirror in Austria, but it doesn't matter really. You can also take Belgium. Usually the rule of thumb is to get a mirror that is close to you. So we should get the Italian one. And but the Italian one, I think it is based in Rome, if I well remember. Milan, Padua, probably Padua is fine, it doesn't matter, you can take whatever. I took the Austrian one in the past because it was the closest in Bologna. Now people made a lot of mirrors, so let's take Padua, but it doesn't make any difference. So, of course, if you take a Japanese mirror, then if it is very far, the web could be less efficient. In the past, there was a big difference. If the server was located in Milan rather than in Naples, you could really see the difference in the past until 10 years ago in the speed of the network. Now, really, the network is so efficient, it doesn't make a big difference. Let's try this. And then, you see, done. There is one more thing that you have to make, because it's installed, but it's not loaded. And the difference is that it's available on your PC, but still not loaded in R. And they didn't make the loading automatic for the reason that I mentioned before, because the more the packages that you load, the slower the PC gets, R gets. So let's load it, because we need it. Because if we don't load it, if now I write help DA-opt-in, I don't find anything, because it's not loaded. So let me load it. Library DA-opt-in. Loaded. Now, if I call the help, I get the help. Okay, let's have a look at the help then. It says that it's a differential evolution optimization. I said before that in principle when you use a software you should know what it does. There are exceptions, of course. In this case we are using an algorithm that is a mathematical algorithm. And in this case, you don't need to go to the references of this algorithm and study the papers. Because, you know, when I say that you have always to know what an algorithm does, this is true for the codes that gives to you the results that you directly use. But if the code, if your rainfall of code uses an optimizator, you don't need to really know what the optimizator is doing, because you have other means to understand if the result of the optimization is correct. You look at the hydrograph and you realize if the optimizator is correct or not. And also you can't study everything. So let's suppose that you use a software that makes the numerical integration. You can't study everything in what you are doing. You have to be efficient in making a selection, learning what is more risky, and of course learn less what is less risky. So if you have softwares like these that perform a purely mathematical task, which you have other means to verify, it wouldn't be productive that you studied what differential evolution, etc. I don't know anything of these methods, because, you know, this is pure mathematics. I understand that it's not easy to follow my advice, because you have to be able to discern what is needed to learn and what's not. But I think that you can get a picture if you use a bit of experience. Okay, so let's see. The usage is we have to use this syntax. We have to write optim, and then there are arguments for this function. The first argument is fn. Fn is the function to be optimized. This is a first problem for us, because we don't know how to transform our code, these steps, into a function, into an arg function. It's easy, but still we have to do that. And then lower and upper are two vectors, because keep in mind that this algorithm can be used to minimize, to optimize several parameters, not just one. We have one to optimize now, but it could be that we had 10 parameters to optimize, which means that you optimize a parameter vector, not 10 separate values for the parameter. You need to put all the parameters into a vector in order to run these softwares. And then what are lower and upper? The lower and upper limits for the parameters. Because it's useful to tell, for instance, the optimizator to search for the runoff coefficient between 0 and 1. It wouldn't be useful if we searched for negative values. So it's very useful to give lower and upper bounds, and in this case, these lower and upper are two vectors, because the parameter is a parameter vector, and therefore also the bounds need to be vectors. The rest of the arguments, you can use defaults. You see, there are proposed defaults. It's easy for us to specify lower and upper, because they are 0 and 1, but we still have to understand how to specify, how to write this function. And the function that needs to be optimized, read here, should have as its first argument the vector of the real valued parameters to optimize. So I have to write a function in R which is to be optimized, and this function should contain as first argument the vector of the parameters. This is what I have to do now. It doesn't take much time, because I already have the written code, and therefore it's easy to transform it in a function. Okay, so I go back to R and I go back to my code, because I need to transform it in a function. Okay, how to write functions in R? First of all, I have to decide a name, and my name would be time area equal function. I am defining a function in R. The argument of the function, the arguments are to be given within parentheses. I have only one argument, which is C. And it satisfies the requirement that the first argument has to be the parameter. Okay, now that I told R that what follows is the function, and the function in this case contains more than one instruction, I have to put all the instructions of the functions between parentheses, the kind of parentheses that we found last time on the keyboard how to get them. So let me close the parentheses here. The problem is that when you define a function, keep in mind that all the variables that you use in the functions are not given back to R. They are deleted, and this is a useful solution because you don't increase the number of variables in R. If you want the function giving back to you a variable, you have to tell the function what is the variable that you want to make. And by using a return. Yeah.
I wrote time area equal to function C, then I went down in order to put the paragraph, but it gives me a plus.
Because you should use, last time we found how to do that. And try to use...
No, I know how to do the paragraph, but why does it give me a plus?
No, you don't have to go in R. I'm writing here on a text editor.
Okay.
This is the next step. You could do that in R, but it's more complicated. Okay, so this is my function. Now we have to do what she was doing. We have to include the function in R. We have to load it. And there are two ways of doing that. Let me adopt the quickest one. Let's copy it, Control C. Let me go back in R and paste it. Done. Now R as the function. So you learned now how to write functions in R. How to check that the function is loaded? If you try to write time area, and you just press return, you get the function again. But what is interesting is to check if the function works. So let me write time area. What is the argument is C. Let me try with a trial value of C. Look, perfect. Perfect. See how it's easy now to find the sum of squares by using the function. Okay, this is perfect. This is the function that we have to give to dA of t. So, let's try. And let me call it like PR is equal to dA of t time area, lower equals 0, upper equal 1. That's it. I pressed enter and you see here It is giving all the iterations.
Excuse me, what is the meaning of PR?
Oh, it's just the name of the variable. You can put whatever you want. You see that it's optimizing. It takes some time, and it prints out the results. You can tell him not to print out the results if you want. And you see that it already converged, because what you see at each iteration is the value of the objective function and the best value for the parameters. It already converged, but it's still trying to explore the whole range between 0 and 1. Let's see if there are, of course, means for telling him not to perform so many iterations. If you think that it is looking for too much details, you can tell it to stop in advance. It's indeed strange that it is taking so much time, but let's try to. We could also stop it already, because it's clear that the best value is 0.049. Okay, I think the maximum number of iterations was set to 200, and therefore he performed all the iterations. Okay, so this is our best value, and we could just make a check. Yeah, you see. Why don't have a look at the hydrograph then? At this stage, we could we could write just C equal 0.049473, and then we can perform our simulation by going back to here. This is our code for performing the simulation. And now we can draw the plot. Okay, let's see the plot how it behaves. Here it is. It's not really great, but still. No, there is something wrong here. Because there is the first part, which is still there, I think. Let me see, just 1 second. No, okay, it's fine. I think it is fine, but still. Let me make a check, just 1 second. I'm not sure on the value of the observer. Okay, let me see now. I rewrite the plot now. Yeah, okay, it was fine. Okay, this is the result. And now the question could be, what happens if instead of selecting the least square as objective function, I select the absolute squares. It's very easy to change it. So let me go back to the code. And you just need to change this line here. Look at what I did. I put I don't know how to say in English. It's a cancelletto sign, an asterisk, and this is this means comment in R. Because I didn't want to delete the line. Okay, and this is I just substituted the square with the absolute value. Then I can reload the function. It's reloaded, and then I start again the optimization. It doesn't change much in this case. It's very similar. The parameter, the best value for C is very similar to what we got before. Let's wait for reaching 200, but it doesn't change much, so I don't think it's worth drawing the graph. Now, if I go back to the graph while it is computing, you see that this hydrograph is not really well reproduced. And in order to get an idea of the model performances, this is not a problem, because I mean I am using a model that is not really the most appropriate one for this case. And also I could change the time area curve if I wanted, but anyway, the hydrograph is not really good. In order to get an idea of what is the efficiency for this simulation, let's compute the Nash efficiency then. And let me, it is finishing, so it's just. Okay, I already have a simulation which is Q. I don't need to recompute it. So, the efficiency can be computed in this way, 1 minus. So, remember that observed is portate, simulated is Q. So, it's, you just need to make sum and portate minus Q squared. To be on the safe side, let me put a parenthesis here. And then I have to divide by sum portate minus mean portate squared. 0.17, which is not good. I told you that below 0.5 is not a good simulation. So, of course, it is reasonable at this stage to say, let's try the diamond.
So efficiency does express the percentage of reliability?
Basically, it's a goodness of fit index that I introduced as an objective function view. And this goodness of fit index, basically I said that it varies between minus infinity and 1. 1 is the perfect model. 0 is a useless model with respect to the mean value as predictor. And so it's not a percentage of reliability, but I may say that the efficiency is very close to the R square of the linear regression. So I'm not sure if you studied the linear regression methods in your previous career, but if yes, you may remember that the goodness of fit index of the linear regression is R squared. Efficiency is very close, meaning that if you make a linear regression between observed and simulated flows, and you compute the R square, it's very close to the efficiency. I think it could be done in R. Basically, I don't remember what is the package for linear regression, but I think it's a record.lin or lin. Let me try. No, this is intelligence. Regression, I don't remember. It's okay. Usual stuff. Okay, I think it is LS fit. Yeah, LS fit. Okay, if you make a dummy variable PR equal LS fit portate Q, in this case I am performing a linear regression between observed and simulated flow. And the result of this linear regression is, of course, the linear regression coefficient, sorry. Coefficients. So if you look at the coefficients,